All right, everyone. So everyone should be able to see my screen now. This is going to be the second module of ECE 4800. And this is going to be a review of vector calculus. And I can't stress the importance of this enough, because electromagnetics is based on a lot of partial differential equations, the Maxwell's equations, that's what they are. And you must know vector calculus in order to be able to understand those. Most of you have taken a course in multivariable or vector calculus before, but just to make sure that we're all on the same page, we are going to review the concepts really from the ground up. And I want to make sure that you all understand this, because it will be very, very important in understanding Maxwell's equations once we start getting into electrostatics and magnetostatics. Okay, so as I said, I'm just going to be checking the public chat every once in a while to make sure that we are that we have any questions or not. And otherwise, if you want to ask any questions, feel free to blurt them out as well. That's also fine. Okay, so here's what we're going to do today. We are going to get into vector algebra. Today we're probably going to get into the addition, subtraction, and then probably the dot product and cross product. We may not even complete all those today, but that's the goal. And eventually we're going to get into orthogonal coordinate systems, and then the meat of vector calculus, which is where you talk about the del operator. We talk about gradients, divergence and curl, how to do surface integrals, how to do line integrals, and all these things will be very important in understanding and working with Maxwell's equations. Okay, just as before, a lot of images are going to be provided from our Ulubi textbook, The Fundamentals of Applied Electromagnetics, and also some images from the Ellingson Electromagnetics open source textbook and the Notaros Electromagnetics. So, as I said, if you haven't had a chance to look at the Ellingson textbook yet, it's free. It's available online. Lots of example problems from there. I even looked at it the other day. I found some really nice problems for homeworks and things like that. So, highly suggested. If you have any trouble with problems in the class, the solutions are there as well. So, it's a really good resource for you to have for extra practice. Okay. Good. So let's start with this. Why do we need vector analysis? So there are many examples of forces and flow fields where the field or the force is expressed as a vector instead of a scalar. So examples of situations where we have something like this, like examples are in fluid flow, electromagnetics, current flows, magnetic fields, and there's also examples in thermal engineering where we look at temperature gradients and things like that. So vectors, let me remind everyone, vectors it's a field that describes spatial variations in a physical quantity. And there's two types of fields. There's a vector field and then there's a scalar field. The scalar field describes a physical quantity which only has magnitude and it has no direction. So an example of a scalar field let's take a thermal system, for example. An example of a scalar field would be temperature. Okay, when we say temperature, we don't say temperature has a certain direction. It's a scalar quantity, so it just has, there's temperature can be defined in a three-dimensional space. Every point in space could have a specific temperature. For example, this side of the room might be hot, the other side of the room might be cold. So different points in space can have a temperature. But that temperature is a scalar, meaning temperature doesn't have any specific direction. By contrast, a vector field describes a physical phenomena that has both magnitude and direction. So the example in a thermal system would be something like heat flux. You know, a vector field would, so for those of you who aren't familiar with heat flux, there's this fundamental relationship of heat conduction is if you have a hot zone, and then if you have a cold zone next to it, heat flows from hot regions to cold regions. So this region might have a certain temperature associated, this region has another temperature which is less than that, and then heat flows from hot to cold. All right, so this flow of heat is called a heat flux. And so it obviously has a direction and a magnitude. The magnitude describes how much heat is flowing. And it turns out that the larger this temperature gradient between the hot and the cold sides, the larger the temperature difference, the more the magnitude of the heat flux is going to be. And then it also has a direction. As you can see, the heat is flowing from left to right in this case. So temperature is a scalar quantity. A vector quantity is heat flux. All right, let's take the example of a fluid system now. A nice example of that is shown on the previous slide here. A fluid vortex, this is what a fluid vortex looks like, better known as a hurricane. All right, many of you have seen these beautiful images of hurricanes from space. I can't help myself, but let's just look one up, right? Hurricane from the space station. I was going to put this on the slides, but yeah, if you've seen like beautiful pictures like these are quite amazing. It shows you really the magnitude and the scale of what these hurricanes look like. These are from the space station. Here's another beautiful shot here. So hurricanes are basically, it's wind, right? It's wind pattern, and these wind patterns form a vortex. And every point in space in that vortex is going to have a certain direction and a velocity. If some of you may or may not know, but that the center of the hurricane, the eye of the hurricane, is actually, there's no wind at the center of the hurricane. Okay, but there are very strong winds once you go outside the center of the eye. Okay, so this is a situation in fluids where we have examples of scalar and vector quantities. So let's go back to this slide here. An example of a scalar field in a fluidic system would be something like pressure. All right, a lot of weather effects are caused by high and low pressure. You hear meteorologists on TV talking about this all the time. So it turns out that the pressure in a hurricane like this, there's a low pressure region in the middle of it. That's part of the reason that hurricanes can form. But that pressure is a scalar quantity. It does not have any direction associated with it. Fluid flow, on the other hand, has a direction associated with it and a magnitude. So jumping back to this slide, we have a hurricane here, and every single point in space here, there's a magnitude of the wind, how strong is the wind, and there's also a direction of the wind. So that's an example of a vector quantity. And we can define mathematically what the vector fields are what the vectors are in every single point in a two-dimensional or three-dimensional space. Another example in fluids is Poisson flow. Whenever you have flow through a pipe, it turns out that the fluid in the middle of the pipe flows faster than the fluid near the walls of the pipe. So this up here and this down here represent the two walls, the upper and lower wall of the pipe. You can think about this in a cylindrical pipe, that this is axisymmetric. All right, but we use vector fields to show how fast the fluids are flowing through the pipe. You can see a large vector here that shows the fact that the fluid is fastest in the middle, and then a zero vector here showing that there's no flow at the walls. Okay, now closer to electromagnetics, of course, we looked at the magnetic dipoles last time in class, and we showed that the magnetic force, the magnetic field vectors point from north to south, and they form these loops. Okay, so there's the force vector points out this way, and every point in space you could actually draw an arrow showing the direction of the vector. So for example, in this point in space, the vector would point just in this direction. In this point in space, the vector would point in this direction. At this point in space, the vector would point in this direction, and so on. So every single point, you can imagine every single point in space has a magnetic field associated with it that has a magnitude and a direction. Okay. There's correspondingly, in magnetic systems, there's something called a magnetic potential, which is a scalar quantity that has no direction associated with it. In electrostatic systems, we gave this example here where we had, back up to this slide, where we had the example of two plates uniform electric field generated between the two plates just by applying a voltage between the two. You have positive charge buildup on one side, negative charge buildup on the other side, and then your electric field looks like this. So every point in space has an electric field. Okay, so I showed the electric field at several points in space here. But I could also pick a random point in space here like this, and that would also have an electric field associated with it. Okay, so every point in space has a magnitude of the electric field, and it has a direction. Electric fields point from positive charge to negative charge. It points from high potential to low potential. Okay, but in this case, these are the electric field vectors, and every point in space also has an electrostatic potential. We are going to find out in the electrostatics chapter, we know that this is 0 volts. Let's say we put 5 volts up here. It turns out that that a point in space here would have a potential of 2.5 volts, right in the middle. A point close to here is going to be close to 5 volts. A point close to here is going to be at 0 volts. And as you go closer and closer to the top electrode, the voltage is going to basically increase. All right? So the analogy is, just as we said, there are, in the thermal system, if we go back to the thermal system, we see how we had high temperature and low temperature, and then we had field vectors, heat flux vectors that point from high to low temperature. Similarly, in the electrical system, we have high potential at the top, low potential at the bottom, and then these field vectors, the electric field vectors in this case, point from high to low. Okay, so there's a lot of analogies in different types of engineered systems where you have scalar quantities and vector quantities that impact one another. One final example that I'll give you today is on chemical systems. So let's say we have, I actually like to show this video, best shown in a video, chemical diffusion. All right. Let me see if I can find the video that I always like to show. Sure, here you go. Skip the ad. More ads. Okay. All right, there's something essential in chemistry called Fick's law, and guess what? It goes from high to low concentration. Very similar to high to low temperature in the thermal system, and electric fields going from high to low potential in the electrical system. So, you guys can take a look at this video later if you'd like in more detail, but the main thing I want to show you is just remind you of, let's see if we can find, where was that part that I was looking for? Okay. Well, let's just skip over that. I'll just draw it here. All right, let's say you have a beaker full of liquid, and then you put just a drop of food coloring in the middle of it. What's going to happen is that the food coloring is going to diffuse outwards. Why? Because this point had a high concentration, and the outer regions have low concentration, right? So all of you have seen that when you just put like food dye in in liquid, right? So in the chemical system, the scalar field is the chemical concentration, and because of that, there's a high chemical concentration in one place and a low chemical concentration in another place. Because there's a concentration gradient, that results in flow of the chemical. So in this case, the chemical diffuses from high to low concentration. That's what's called chemical flux. And this can be also known as diffusion. All right? So there really is a lot of beautiful analogies between the different types of engineering that we often study. We focus on electrical systems, but the same sets of equations can actually be applied to chemical systems, fluid systems, and thermal systems. So the stuff that you learn as an electrical engineer can actually be applied if you end up doing other aspects of engineering as well. Okay, So let me jump back to our conference here and see if there's any questions. Thanks, Joseph. Yeah, the sugar I just put in my tea, I believe the sugar diffused. Absolutely. Absolutely. Yeah, and you actually enhanced the mixing by stirring the sugar into your tea, and that is a separate phenomena called convection. Convection can also be described by vector fields. Oh no problem. I totally get what you're saying. So, I just want to impress upon you that every single field of engineering has vector and scalar fields. Of course, we are going to be focused on the electromagnetic ones. All right, but for the purpose of this chapter, we are going to be, we're not going to be limited to just electromagnetic systems, because we can review the concept of scalar and vector fields in this way. All right, so getting to the fundamental things now, what is a vector? So this is going to be very basic for many of you, so just bear with me, but I just want to make sure that we all start from the ground up on fundamental concepts. Okay, a point is used to represent a physical location. So if we have a xy axis, two-dimensional axis here, you have the x coordinate A and the y coordinate B. If you're in a three-dimensional coordinate system, then you have x, y, and z coordinates, but it's used to represent a physical location. In contrast, a vector, it doesn't really correspond to a physical location. Instead, it just has magnitude and direction, right? And it's used to represent a force or a flow. So a vector will be an arrow like this, whereas a point is just a point. The vector has, in this case, it has two components, because we are looking at just a two-dimensional Cartesian system where the vector has an x coordinate and an x component. We call this an x component and a y component. All right, we're here with the point. We say this has the A is the x coordinate and B is the y coordinate. Here we say the x component is A and the y component is B. All right. So one of the things that we often we forget is that a vector doesn't have a physical location. It's an arrow. Okay. In a vector field, you have vectors at very specific locations, but that's in a vector, that's a vector field. Okay. Just a single vector on its own just has magnitude and direction. All right. Now you can also calculate the angle of a vector, just to remind everyone. If you're given a vector with the coordinate with the magnitude v, for example, you can figure out the x and y components. In a two-dimensional system, the magnitude is given by the square root of a squared plus b squared, Pythagorean theorem. So this is what we're denoting as the magnitude of v, the length of that here. So let's see. Let's give an example here. Let's say this is equal to 2, and this is also equal to 2. All right. Then we know that this is a 45-degree triangle. The magnitude of v is equal to the square root of a squared plus b squared. So 2 squared plus 2 squared. This is 4 plus 4, 8, square root of 8. All right, which is also equal to 2 square root of 2. You get that right? Yep. Okay. Now, so in a three-dimensional coordinate system, you would do something similar. The magnitude is equal to a squared plus b squared plus c squared, x, y, and z components. All right, the angle gives the direction of the vector. So, we already know that when you have this type of triangle where a and b are both the same, that's a 45-degree triangle. But you can calculate this angle by taking the inverse tangent of b over a. Okay, so in this case, if you wanted to find angle of v, let's just put it out here. Angle of v equals arctan of 2 over 2, and if you put that in your calculator, you find that's equal to 45 degrees, or pi over 4. Okay, good. So this is all like fairly simple. Let's see these questions. All right, good. So next, we have the magnitude and the angle here. The unit vector, just to remind everyone what the unit vector is, every vector has a corresponding unit vector. So let's say you have a vector pointing out in an arbitrary direction, that's v, and the unit vector will point in the same direction as v. It'll have the same direction, it'll have the same angle, but it will have a different magnitude. The magnitude of the unit vector is always equal to 1, okay? So the magnitude of the unit vector is always equal to 1. So if we let's take a quick example of the one that we just did. So let's say we have a vector that looks like this. So we can denote that vector 2, 2. This is the x direction, and then this is the y direction. All right, so the way that we can denote our vector is in two ways. So we can say v is equal to 2, 2. And that's a shorthand way of saying, that this is equal to 2 times x hat plus 2 times y hat. Okay, both of these are equivalent forms of what the vector is. This means that this is the unit vector in the x direction, and this y hat is the unit vector in the y direction. So they're basically telling you the x and y components of the vector. All right, so if we want to find the unit vector here, the unit vector, which is denoted with the little hat symbol on top of it, it's equal to v. So this will be 2x hat plus 2y hat divided by the magnitude of v. So let's calculate the magnitude of v. Actually, we found that on the previous slide already. All right, the magnitude we calculated as 2 root 2. So this will be 2 square root of 2 at the bottom. Okay, so we'll show the property that you can use to solve this. I'm just going to solve this right now, as you all can see. So we can think about this as 1 over 2 square root of 2, 2 times x hat plus 2 times y hat. And these will cancel here. So you just distribute this out to the x and y terms. And so you will get x 1 over square root of 2 x hat plus 1 over square root of 2 y hat. So this is your unit vector v hat. Okay, and if we want to check, did we do this right? One thing you can always do is check to make sure that your unit vector has a length of 1. So let's check and make sure we did that right. So we're going to just move over here and this, we can squeeze it in here. So let's find the magnitude of v hat. So it's going to be the square root of a squared plus b squared, the x and y components. So it's 1 over square root of 2 squared plus 1 over square root of 2 squared, square root of this. So this is 1 half square root of 1 half plus 1 half. And that's the square root of 1, which is equal to 1. Okay, so this is a way of confirming that your unit vector is indeed a unit vector. It should always have a length of 1. Excuse me for 1 second. Okay. All right, good. Let's see, any questions? Any questions? Give me a thumbs up if we're all on the same page here. Okay, great. Okay. Good. Thank you. By the way, if you want to maximize my slides, you can click on this portion here to make your screen share full screen if you want to be able to see the slides in the largest format. Awesome. Okay, let's move on then. So vector addition. This is obviously important because a lot of times we have situations where you have multiple forces acting on an object and we want to add the different forces together. In electromagnetics, we have situations where we have the principle of superposition, where you have multiple electric fields acting on an object, or multiple contributors to an electric field. In order to find the total electric field at that position, you have to be able to perform vector addition. So here's an example. You have two arbitrary vectors, A and B. So imagine that A has the components x1 and y1. B has components x2 and y2. And the sum of the two vectors, the way that you can visualize that is imagine that you take this vector A and you just put it here in space, and then you connect the second vector to the first vector. The convention that's often used, they say, is head to tail. So we say this is the head. This is the head of the vector. And this is the tail of the vector. All right, so when we say head to tail, that means the head of B attached to the tail of A. All right, so that's the tail of A, and then this is the head of B. Okay, so you arrange the two vectors according to this head to tail convention, and then the sum of the two components, A plus B, is going to be going from the head of A to the tail of B. Okay, so that's visually what's happening, when you sum up two vectors. And mathematically, you're just summing up the x components and you're summing up the y components. Okay. All right. So vector subtraction. Some of you may or may not recall the physical or the graphical representation of vector subtraction, so I'll just go over that real quick. So again, imagine that you have two vectors A and B, where you have A is equal to x1, y1, B is equal to x2, y2. A minus B, the mathematical definition, is quite straightforward. It's a new vector with the x component equal to x1 minus x2, y component equal to y1 minus y2. But visually, what does this mean? All right. So one way of thinking about it is, again, we use this head to tail analogy. So this is the head of A, and then this is the tail of A. So here we have the head of A. I'm sorry. It's the tail of A. The tail of A and the head head of B. Okay, so this is this vector here, as we saw before. This would be A plus B. All right, but if you take B, if you take this B vector here, and you just negate it. So what does it mean to negate a vector? It means that you find the mirror image of it. You reflect it across both axes. So what does that mean? Let's draw this out here. So let's say we have our x and our y axes here. This is x, and this is y. Oops. Okay. So what we do is we take this vector here, we reflect it across the y-axis. If we reflect it across the y-axis, it would look like this. Reflect it across the x-axis after that, then it looks like this. All right, so this is negative b over here. Okay, just for clarity, let me erase this line here. So when we find the negative of a vector, what we are doing is we are reflecting it across the x and the y-axis, or in other words, we are reflecting it across the origin. Okay, this is in a two-dimensional coordinate system. The same type of thing would apply to a three-dimensional coordinate system as well. We're reflecting it across the origin, reflecting it across the x, y, and z axes, all three axes. All right, so if we take b here, so let's see, so this is our b vector here, and we take the negative of that, so this is negative b. So a minus b is going to be equal to the head to tail of the a vector and then the minus b vector. Okay, so this is going from the head of a to, and this is the tail of negative b. Okay, oh, I'm just skipping over a lot of stuff here. Okay, so hopefully this makes some sense. So this is a graphical representation of a minus b. Okay, so let's discard those. This is a simple example of vector addition, and you know, just to keep this lecture from being a little less boring, I put my favorite Star Wars characters in here. Let's say that there's a lightsaber, and you have Darth Vader over here. He's pulling the lightsaber using the force at a 30-degree angle, and he's pulling it with a force of 3 kilonewtons. Okay. And then suppose Yoda over here. Yoda is, the Jedi Master, so he can pull with a greater force. He's also pulling at a 30-degree angle with respect to the horizontal over here, but he is pulling with a 4 kilonewton force. And then we have Luke. I couldn't find an old picture of Luke from the early 70s movies when Star Wars first came out. That was one of my favorite movies growing up. So, but they have I found this picture online where he's in his in his more middle-aged state. So he's only pulling with 2 kilonewtons because I just don't think he has the same level of capabilities as Vader or Yoda does. You may or may not disagree, but this is just an example problem here. All right, so Yoda is pulling with. So what we can say here is that the magnitude of this vector here is, we can call this 2k, and k is just shorthand for 2000, and this will be 4k here for Yoda. So the length, when we're talking about magnitude, we're talking about simply the length of the vector here. All right, and Vader is pulling with 3 kilonewtons, so the magnitude of this vector here is going to be like this. So 3k here. Okay, this is a good example because it shows the, it talks about why vector addition is important. It also reviews some, just some basic geometry things that we often use when we're analyzing vectors. And it shows how to just, bring all the concepts together, figuring out the magnitude, the x and y components, how do you add up the vectors, and so on. Okay, so we are going to do this. I have the solution out on a different slide, but in order to show you step by step, I'm just going to go through it here like this. Okay, so the first thing we want to do in this problem is we want to break down each one of the forces. We want to find the vector equations for each one of the force components. So in other words, we have F Luke, F Vader, and then our favorite Yoda. All right, let's figure out the Luke's force first. So we're going to redraw this thing here. So we imagine that the lightsaber is at the origin, and there's 3 forces acting on it. So the first force is this is going out at a 45-degree angle. Right, from what we saw here, it's a 45-degree angle, and this is 2,000. Okay, and so from our geometry here, so this is a 45-degree triangle. So we know that, we know from geometry that this would just be 2,000 over square root of 2. Okay, 45, 45, 90 triangle. This is x, and this is x square root of 2. That's our 45, 90 triangle. The mathematical way that you can do this, I'll show this here, is F Luke is equal to, you have an x component and a y component. So the x component, x hat, you multiply this by, if we want to find the magnitude, the length of this portion of the vector, then what we would do is we would take, let's make this here. It would be the hypotenuse times the cosine of 45. So 2,000 times the cosine of 45 degrees plus y hat times 2,000 times the sine of 45 degrees. Okay. All right, so this will then come out to, we can write this in a shorthand. We can say 2,000 1 over square root. Actually, we can say 2,000 over square root of 2 x hat. Oops. X hat plus y hat. Okay. All right. So the next component is going to be, let's do Yoda next. Where this has twice the magnitude, so it's 4,000 here. And this one, I'm just going to delete this here to make room. So this is at, let's remind ourselves, let's look at the diagram again. This is at a 30-degree angle. So 30 degrees here. It's a larger magnitude. Okay, this is our 90 degree here. This is, this is a 30, 60, 90 triangle. So let's remind ourselves what a 30, 60, 90 is. I know a lot of this is very basic for many of you, but I think it's always good to just remind ourselves of things we may or may not have forgotten. So this would be x, 2x, and x times the square root of 3. These are the proportions of the lengths in a 30, 60, 90 triangle. All right, so the side that's, 4,000 is equal to 2x, then we know that this side is equal to 2,000, half of that. And then this 60 side would be 2,000 square root of 3. All right, if we write it out mathematically, let's say, so what I want you to be careful about here is the signs, okay? Because we know that this x component is going to be positive, but the y component is going to be negative, okay? So let's be conscious of that when we write out these equations. So x hat, this is going to be 4,000 times the cosine of 30 plus, no, see that, I made that mistake, minus y hat. This is a negative direction, you see here, minus y hat times 4,000 sine of 30. Okay, and if you do if you actually do the math here, you'll find what we found intuitively earlier. So let's see, we can write this in a compact form. Let's see, 2,000 square root of 3 times x hat minus 1 times y hat. Okay, let's see everyone with me here. If you make a mistake, where's Palpatine? Yeah, that's I should have included him on here. But if we included a fourth character, then 3 is already long enough. We're doing a lot of calculations here. But I welcome you to add Palpatine to this and see how the forces play out. All right, let's do Vader now. This is 30 degrees. All right, and this was 3,000, the force in this direction. So we have 3 vectors here, right? We have these 3 vectors, and we're going to take the sum of all of them. So this is a 30, 60, 90. So this is going to be, the 30 degree side is going to be 1,500. And this is going to be 1,500 times the square root of 3. And just to totally belabor this, we will just do this mathematically as well. Again, being mindful of the direction. So we know that this is going to be in a negative x direction and a negative y direction. So let's just put that in there, negative x hat. So this is going to be 3,000 cosine of 30 minus y hat 3,000 sine of 30. Okay, and the total here is going to be 1,500. 1,500 negative square root of 3 times x hat minus y hat, like this. All right. So we did the hard part here. We figured out all the force components. Okay. The initial version of the problem that I had in the older version of the notes, I updated the notes here because I wanted to include this here. I actually had written out the x and y components of each one. But you know, part of when we get to electrostatics and we have a distribution of charges, we're going to want to remind ourselves how to calculate each one of these force components just using the basic geometry things that we learned in high school and so forth. So now that we have the different force components, we can add them up. So let's do the total force. We can call this Ft. T for total is going to be equal to the force from Luke plus Yoda plus Vader. Remember, the thing we're trying to calculate here is what is the net force and what is the net direction that the lightsaber moves. Okay. All right. So 2,000 over square root of 2. So what we're going to do here is we're going to add up all the x components. So to be totally clear here, let's do x1 plus x2 plus x3 so that we're going to add up the x components here, and that's going to be the x component of the total vector, and we're going to add up the y components, y1 plus y2 plus y3 y hat. Okay, so we add up the x component of Luke here, which is 2,000 over square root of 2, plus the x component of Yoda, 2,000 times square root of 3, plus, we have a negative sign here, so let's delete that. Vader is minus square root of 3 times 1,500. So these are going to be our x components. Then we look at our y components here. 2,000 over square root of 2 plus 2,000 times square root of 3 I'm sorry, I made a mistake there. Minus 2,000. So this is the component of Yoda, 2,000 times negative y hat here. And then the for Vader, we have 1,500 times minus y. So okay. All right, and if we add all these up, someone with a calculator can help me out here, or I'll get my own calculator out. Give me a minute here. I'm going to calculate this. All right, so 2.28 times 10 to the third is the x hat component. 2000 divided by square root of 2 minus 2000 minus 1500 minus 2.09 times 10 to the third times y hat. Okay, so this is our total force. And I'm just going to skip ahead here. Let's see, I think I had here's the solution slide here. Okay, and I must have made some kind of calculation error here because the numbers I got here were different. 1.9 x hat minus 4.7 y hat. I'm not going to bother like fixing up the calculations because the process is really what's important here. So what I want you all to see here is that once you have the total force, what we're interested in finding is that what is the net force on the lightsaber and what direction does the lightsaber move. Okay, so again, I'm not going to bother like figuring out like what if I made a small calculation error here. I want you to understand the process. You add up the total forces here, and you get an x hat and a y hat component. What you can see here is that the x hat component is in the positive direction, the y hat component is in the negative direction, and so the net force looks something like this. And the way that you can find the angle of the net force is to do the arctan inverse tangent of this negative y component. So 4.7 over negative 1.9, and you will get an angle of negative 67 degrees. So this angle here, this angle of the force would be negative 67 degrees. Okay. So this is the direction that the actual lightsaber would move. All right, let's go back if we have any questions. Okay, other than where's Palpatine? Okay, any other questions? Please, please put it on the public chat. Okay, let's see where we're at now in terms of time. It's about 10:30. Okay, good. We can continue then. So now we want to get into vector multiplication. So there's three types of vector multiplication, and each has a distinct physical meaning. So scalar multiplication multiplies a vector with the vector. It multiplies a scalar with the vector, and the result is a vector quantity. Another type of multiplication is the dot product. This is where two vectors are multiplied together, and the result is a scalar. And then there's a third type of multiplication, which is called the cross product. This is where you multiply two vectors together, but you get a vector as a result. Okay, now, so we're going to go over each one of these three in turn. The first one is scalar multiplication. So suppose we're given a vector A and a scalar n. So let's say we're working with a three-dimensional vector now. So you notice that there's three components of the vector A: ax, ay, and az. So this is the x component, the y component, and the z component. So if you multiply a vector by a scalar, what it essentially does is that it has the resulting vector has the same direction but a different magnitude. So if this was a vector A and you multiplied it by 3, you'd get 3 times the magnitude of the vector, but it has the same direction. That's the key point here. When you do scalar multiplication, the resulting vector has the same direction, just a different magnitude. Okay, so now we go on to the dot product here. Dot product can be defined in 2 dimensions, 3 dimensions, 4 dimensions, and so on. And the reason why dot products are important are because of something called projections, and that's what we'll go over on the next slide. Okay, so let's first talk about what the definition of the dot product is. So in two dimensions, the dot product is defined as A dot B. And suppose you have a vector A and a vector B that's defined as AX and AY, BX and BY. The dot product, and the way that we denote the dot product is with this bullet here. Okay, it's just a dot or bullet shape. A dot B, we say A dot B is equal to AX times BX plus AY times BY. So you notice what we did here, right? We just took these two components, multiplied them together, added it to these two components multiplied together. Okay, and the same thing would hold true for the three-dimensional dot products as well. The three-dimensional dot product denoted A dot B is equal to AX BX, so you multiply these two together. AY BY, you multiply these two together, and then AZ BZ, multiply these three together. And again, I'm just going to emphasize that. Notice that this is a scalar quantity, scalar, in the two-dimensional case and also the three-dimensional case. Okay, so we took two vectors and we multiplied them together and we got a scalar quantity. A scalar quantity has no direction, so we're going to look at what that means in a second. But let's look at a simple example here. So we have a vector A is equal to 1, 2, 1. B is equal to 3, 4, 3. The dot product, you multiply 1 and 3 together, you multiply 2 and 4 together, and you multiply 1 and 3 together. And that's what you see here. You add up all those things together. So 1 times 2 plus 2 times 4 plus 1 times 3 is equal to 13. And that is a dot product of A dot B. Okay, quick question now. Can everyone hear me okay? There's a little bit of noise in the background, so just want to make sure that everyone can still hear me. Okay, I see one yes, so I'll just assume that everyone can hear me. Okay, good. Okay, so let's talk about what the physical meaning of the dot product is. So mathematically, the dot product is defined as A dot B is equal to the magnitude of A times the magnitude of B times cosine of theta. Okay, so we have two mathematical definitions. So one that we saw in the previous slide, which tells us how to calculate the dot product, and this is giving a second definition of the dot product here. Okay, and this is saying that the dot product of A and B is equal to something. It's equal to the magnitude of A, magnitude of B times the cosine of theta. And we can represent that graphically and sort of get a physical intuition of what the dot product means, or geometric intuition. So geometrically, the component of A and B, well, let's get to the components in a second first. So let's write this down here. So this is, suppose we have a vector A. So this is our vector A, and then this is our vector B. Okay, so this length is the magnitude of A right here. Okay, and this length here is the magnitude of B. Okay, and what you can see here, this portion here is A times cosine of theta. All right, so remember the cosine of theta would be equal to this quantity over the hypotenuse. So this leg of the triangle is equal to magnitude of A times the cosine of theta. All right, so this is the component. This is equal to the component of A on B. All right, the length, I'm going to make a note here. The length of this leg is the component of A on B. All right, and that's what it says up here. The component of A on B is equal to the magnitude of A times the cosine of theta. If B happens to have a length of 1, then A dot B is the component of A on B. The way we denote that is component. This is a little bit confusing here, so let me explain this. The component of A on B, the way you denote that is the component, and you have your A here, and your B is a subscript. So the way it actually reads is the component on B of A. It's a little bit confusing, but just so you know. This is the component of A on B. Okay. And if B happens to have if B happens to have a magnitude of 1, then this is going to be equal to the dot product of A dot B. All right. Another way of saying it, which could be a little bit more clear, is that the component. Well, let's write this over here. The component of on B of A is equal to A dot B divided by the magnitude of B. Okay, so I'm going to put a box around this, so this is an equally important formula. This is how the dot product is related to the component. Okay, let's talk about why components and projections are important. So one way you can think about components is that, let's say you can think about it as kind of like a shadow. So let's say I had light. Let's say I had a light source coming in from here. That light source happened to be orthogonal to B. The component of A on B is equal to the length of the shadow that's cast from A to B. So let's talk about what that means. You know, the light, here, let me switch over to here. The light sources is coming down this way, and let's say the vector A is kind of like, you know, something that that causes a shade. It blocks the light. So you know, then the light sources. Let's just erase this. Light sources are all coming down like this. Okay, so the light is blocked by this. Imagine that you have, you know, that whatever this vector is, the length of that vector happens to be blocking some of the light, and so the region that is blocked, that is the shadow cast by the vector A on B, and that's also defined as the component of A on B. Since I deleted that, let me just write this out again. Component on B of A is equal to A dot B divided by the magnitude of B. Okay. Some of the properties of the dot product. These properties can be proven with basic algebra. A dot B is equal to B dot A, commutative property. The magnitude of a vector, A dot A, is equal to the magnitude of A squared. And then a third one, if A and B are perpendicular, then A dot B is equal to 0. And you know, these are very easy to prove. Let's say we have a vector A is equal to x1, y1, and then a vector B, x2, y2. All right, so A dot B is equal to x1, y1, oops. x1, x2, comma, y1, y2. And of course that's equal to b times a, which is x2, x1, y2, y1. Excuse me. All right. The next one, if we do a dot a, you can see that a dot b is equal to b dot a. All right, if we do a dot a, then it's just equal to x1 times x1 plus y1, y1. So this is x1 squared plus y1 squared. Let's remind ourselves what the magnitude of a is. The magnitude of a is equal to the square root of x1 squared plus y1 squared. So a dot a is just equal to the magnitude of a squared. You can see x1 squared and x1 squared and y1 squared is the magnitude of a squared. All right, and the most important one, a dot b, if they're a and b are perpendicular, then a dot b is equal to 0. This rule is used quite a bit, so please remember that one. That one's super important. And the way that you can prove this one, I'll just write it down here, a dot b is equal to a, magnitude of a, times the magnitude of b, times the cosine of theta. Now, if theta is 90 degrees, we know that the cosine of theta is 0. So if theta happens to be 90 degrees, this whole cosine of theta will be equal to 0, and then a dot b will end up being equal to 0. So if theta is 90, then the cosine of theta is equal to 0, and the whole thing ends up being 0. All right. So this is some simple things with the dot product. So the reason why that's important is when we do three-dimensional vectors, a lot of times the question will come up is, are these two vectors perpendicular to each other? If they are, the easy way to test that is just to see if their dot products are equal to 0. All right. So let's talk now about projections and components. We talked a little bit about components. Let's talk about the projections now. As I said before, so imagine that you have a vector A and then you have another vector B. So you have two arbitrary vectors. And if you want to figure out projections and components, the first thing you do is you draw this orthogonal line connecting the two. So it goes from the tail of A, and then it is orthogonal. You draw a line that's orthogonal to B. Start at the tail of A, first arrange A and B so that the heads are together. The second thing is you draw an orthogonal line going from the tail of A down into B so that it's orthogonal to B. So from there, you can figure out the projection and the component. So let's define what those are. The component we already defined before, so let's start with the second one here. Okay, the component is basically the distance from where my mouse is here to where my mouse is here. So it's the distance of this leg of the triangle. And the vector is basically the length multiplied by the direction, the unit vector of B. All right, and it's graphically shown here. If you have a vector going from this point to this point, then that is the projection of A on B. Projections turn out to be important because we often want to figure out the forces in a certain direction. We'll talk about that on the next slide. Okay, but let's figure out how to calculate these now. The component of B on A, this is what I showed in the previous slide, is equal to the magnitude of A. So this leg here times the cosine of this angle theta, and that turns out that that is equal to A dot B over the magnitude of B. So that's the length of this red line here, this red arrow, the length, the magnitude of this line. All right, note that the component is a scalar quantity. Now we figure out the projection. The projection of A on B, remember that funny notation here, the B is in the denominator. This is equal to the component of A on B times B hat. Okay? Now the way to think about this is a funny formula, but the way to think about this is that this is the projection that is a vector that points in the direction of B, but the length of that vector is equal to the component of A on B. So this is the magnitude of the vector, okay, component of B on A, and then this is the direction, B hat. Remember that B hat has a magnitude of 1, right? So B hat is essentially giving you the direction of the vector, and this portion is giving you the magnitude of the vector. Okay, so the way that we then figure that out is, we already know that the component of B on A is equal to A cosine of theta. Okay, so that's how we get this portion here. And then we know that the we know that A bar cosine of theta, if we look at what B hat is, let's remind ourselves what the definition of B hat is. B hat is the magnitude of B, B hat is equal to B divided by the magnitude of B. Okay, so if we just substitute this in here, then we will end up getting what we see here. It'll be equal to A dot B times A divided by the magnitude of B squared. All right? Okay, good. So now we have a simple way of calculating the projection and the component of A on B. So if we do a simple example of that, we can go through the steps here. Suppose we have a block that rests on an inclined plane of angle theta, as shown, and gravity provides a force F equals 0 times negative mg on the block. So the question here is, what will be the component of F in the downhill direction, and what is the projection of F in the same direction? This is a very simple problem that you'll get in any physics type textbook, but it illustrates the importance of components and projections in a real world scenario. So the problem that we have here is that we have, let's say we have a truck. Let's say this blue object happens to be a truck, and it's sitting on an incline. And we want to see, like, how much force what is the force of that truck in the downhill direction? If we want to know like how strong the parking brakes for that truck should be to ensure that it doesn't start rolling, we would want to figure out what is the force of that truck just in the downhill direction. Now, intuitively, you can think about if the truck were completely vertical, there's going to be a high force. And of course, if the truck is, we're looking at the force in the downhill direction. So there's going to be a huge force if the slope is 90 degrees. But if the truck is in a horizontal plane, then the force is going to be equal to 0. There's going to be no downhill force on that truck. So this is why projections and components are important, because what we know in this problem is that we know that gravity is always acting in this negative y direction. So this force is equal to m times g. So the gravitational force F is equal to m mass times acceleration, and then the acceleration on Earth is g, so it's just m times g. All right. So we don't care about the force going in the negative. We already know the force going in this y direction because that's just the gravitational pull. What we're interested is the force in the downhill direction. So this is an example of where we have to use projections and components to figure that out. So the first question is, what is the component of F in the downhill direction? So this is a solution here. So we note that F is equal to 0 times negative mg. A vector pointing downhill, as shown, is d equals cosine of theta negative sine of theta. All right, let's see what's going on here. Where did they come up with this? So what they're finding here is they're trying to find the unit vector. First step is figuring out the unit vector in the downhill direction. So you have this angle theta. All right, and what we're trying to find is the unit vector of d. So d hat. Let me just delete this for a second here. Okay, so we do a triangle here. If the length of the unit vector is equal to 1, then this leg here is going to be equal to the cosine of theta times 1, or just the cosine of theta. And this leg here is going to be equal to the sine of theta times 1. And this is going to be in the negative direction here. All right, so what we did here is we found the unit vector in the downhill direction, cosine of theta, negative sine of theta. So the next thing we have to do, so this is step 1. The next step is finding the component. So step 2 is finding the component of F along D. Okay, and then as we found on the last slide, the component of F on D is equal to F times D over the magnitude of D. All right, so that's relatively easy to calculate. So let's remind ourselves, what is the component of F along D? What does that mean physically? So we have the force going in this direction. The force is going in the negative direction, but we want to find how is gravity affecting the downhill force. So essentially what we want to find is the magnitude. We want to find the magnitude of the force in this downhill direction. What is the component? The downhill force is going to have a horizontal component and a vertical component. We want to find the vertical. We want to find we want to find D by knowing F, and then through the components and projections. So the component of F along D is equal to this. So first we find the dot product here, F times D is equal to 0, negative mg. This is the force of gravity, dotted with cosine of theta, negative sine of theta, and that gives us mg sine of theta. All right, so that is the component of the gravitational force in the downhill direction. So the magnitude of d we know is equal to 1. So the next step, we find that the component of d on f is mg sine of theta. Actually, this is all part of the same step. So the next part is, this is figuring out the component of d. So that's part A. Part B is figuring out the vector projection. Remember that the vector projection is going to have the same magnitude as the component that we just calculated, but it's going to be in the direction of d. So all we do is we take this thing here. This is the magnitude here, and then the direction of d is, we found up here. All right, so the vector projection of d onto f, this is the mathematical formula for it. It's the force dotted with d times d over d squared. But notice that we don't actually need to do all these calculations here. We've already computed a lot of these things. So essentially what we're doing here is we know that the projection is, the magnitude of the projection is equal to the component that we just calculated, and the direction is equal to the unit vector along in the d direction. So here is the magnitude, and then this vector is a unit vector that gives the direction. Okay, so this is just a quick way to find it. If you want to go through and use this formula here to calculate the projection, that's also fine. Okay, I'm just trying to speed things up a little bit in the interest of time here. So I highly recommend that you go through this problem at home, understand how to do it, understand what it means, and this will help you understand the concept of projections here. Okay, good. So there's some more examples of vector multiplication here that I think I'm going to have you all do as an exercise. Suppose we have two vectors, 1, 2, 3, 4, 5, 6. So calculate a dot b, calculate b dot a, calculate the magnitude, calculate the unit vector, and the projection and the angle between them. I think it might actually be helpful to just do this real quick together as a class, and then in your homeworks you'll be asked to do some similar problems here like this. So let's just go through this really quickly. A dot b is equal to 1 times 4 plus 2 times 5 plus 3 times 6. So 4 plus 10 plus 18. So 18 plus 10 here is 28, plus 4 is 32. Okay, what is b dot a? Well, we know that b dot a is just equal to a dot b. So this is equal to 32. The magnitude of a, this is also fairly straightforward to calculate. The magnitude of a is the square root of the sum of squares of the different components. 1 squared plus 2 squared plus 3 squared. So this is the sum, 9 plus 4, 13 plus 1 is 14. So this is equal to the square root of 14. Find the unit vector a. So the unit vector a hat is just equal to a divided by the magnitude of a. So this will be 1 over the square root of 14. Multiplied by 1 times x hat plus 2 times y hat plus 3 times z hat. Okay, so that's the unit vector, the projection of A on B. So the projection of A on B, just to remind ourselves, projection of A on B is equal to A dot B times A over B squared, and then the component is A dot B divided by B hat. So let's just do that real quick. So the way that we find the projection, I think the easy way to do it is find the unit vector of B. So the unit vector is going to be equal to B divided by the magnitude of B. And that's equal to, let's see, so 6 squared, 1 over 4 squared plus 5 squared plus 6 squared. That's the magnitude of B, times 4x hat plus 5y hat plus 6z hat. And now you find the component of A on B. Okay, and that is just equal to it's equal to A dot B over the magnitude of B. So this is equal to 32 over the magnitude of B we found was, we never solved it, but I'm just writing it down here real quick, 4 squared plus 5 squared plus 6 squared. Okay, so now to find the projection, we have the magnitude. The magnitude is equal to the component of B on A, and the direction is equal to this. So we multiply the two together. Projection of B on A is equal to the product of these two, B hat times the component of B on A. Okay, when we multiply the two together, we will end up getting 32 over 4 squared plus 5 squared plus 6 squared times 4 x hat plus 5 y hat plus 6 z hat. All right, so there's our projection of A on B. And then finding the angle between the two, I'm going to squeeze that in here. So if we want to find the angle, this is how we do it. So we use A dot B is equal to the magnitude of A times the magnitude of B, times the cosine of theta. So the angle between them So we already know the magnitude of A and B. We calculated both of those earlier. So what we can do here is we say the cosine of theta. Actually, we'll go one step even further. Theta, the angle between A and B, is equal to cosine, inverse cosine of A dot B over the magnitude of A times the magnitude of B. Okay? Oops. And so, because we're running out of space here, I'm not going to bother to do the math here. You can figure this one out. Okay, we already found the dot product here is 32. The magnitude of A is the square root of 14 here. The magnitude of B is the square root of 4 squared plus 5 squared plus 6 squared. You take the inverse cosine of that, and you'll find the angle between them. Okay, much easier to find the angle using the definition of the dot product than to try to do it geometrically. All right. Let's see questions. Okay, here's a good question here. How would you draw the component of B on A? Okay, great question. And I think I'll answer that question, I think. And if there's any other questions, please write them down here, because I think what we can do is spend the last 4 minutes of class on questions like this. So let's do this first one first. Arad asked, how would you draw the component of B on A? So let's back up here. All right. So I'm going to go ahead and erase some of this extra stuff. All right, so this is the component of A on B. Now, if you wanted to do something similar, you want to draw the component of B on A, this is how you do it. So this is our B vector, and this is our A vector. Okay. So what we do is we start off with the tail of B. So this is the point that we start off with, and we draw a line onto the vector A that's orthogonal to it. So because B is larger than A, we actually have to extend A out a little bit, like this. Okay, now imagine that we draw a orthogonal line like this. Nice 90-degree angle there. And the length of this component so the length here, the length from this point to this point would be considered the component of B on A. Okay, and mathematically the formula, the component of B on A would just be equal to A dot B over the magnitude of A. Compare these two formulas here. Component of A on B on the left side, and then the component of B on A here on the right side. Okay. The denominator is the only thing that's different. Great question. Let's see if there are any questions. Any homework for the next class? Yeah, Falak, that's a good question. I am going to be assigning a homework tonight. It's going to be on Module 1, what we finished up last week. And I'm also planning on having just a short question on some of the vector addition stuff that we covered today. And that's going to be due next Wednesday in class. Next question, Siva is asking, do we have a quiz coming up? We don't have a quiz coming up, just the homeworks right now. Just keep in mind that we have the first exam is going to be, it's listed in the calendar. That's coming up in probably a few weeks now. I see Falak is typing something. Falak is asking, is the next class, is it in class and not online? No, I want to clarify to everyone that the next week's classes, Monday and Wednesday, will actually be online as well because I'm going to be at a conference. So please plan to log into Big Blue Button. We'll just do the same as before on Monday and Wednesday. If I have some sort of scheduling conflict, what I may do is pre-record the lecture and just put it on YouTube and have you all watch it. I prefer not to do that, but if I end up having a scheduling conflict during the conference, that's what I'll do. If you have any questions on any of this material, please do send me a question, send me an email and ask. Homework will be posted. The lecture will also be posted on YouTube probably by the end of the day today. If you have any friends who are not able to attend the class today, please let them know that the lecture is posted on YouTube and that we have the homeworks. I hope everyone is able to turn in the homework to Stephanie Toland at the front desk. And if you have not yet, just go after class and go turn it in. I won't penalize you for it, just so everyone gets a chance to get their homework in. If you have any questions, concerns, please let me know. Joseph, thank you for the lecture. Thank you. Thanks, Joseph. I appreciate it. Falak, thank you also. If you have any feedback on, if you have any concerns with how the online lectures work, please let me know. If you're happy with it, also let me know, and so that doing this hybrid kind of format won't be. I'll consider it to not be an issue then. Okay, we'll just finish up. I'm just waiting for a few. Okay, Noor, Naum said you like the online format. It's good. Okay, excellent. So if there's any concerns about it, please feel free to email me. And otherwise, I hope you all have a great day. As Joseph is saying, we should just make this an online class. I will be happy to do that when I'm traveling. Although I think some things like having regular lectures in class is helpful in my opinion. If you all have strong opinions on that, send me an email. I'm not stuck in any one way or another. Yeah, pajamas is great. I've actually given online lectures. I gave a lecture to the National Science Foundation, and it was a web recording, so I had a nice shirt on and I had pajamas on and slippers at the bottom. So one of the advantages. If we do have days where there's a lot of snow or if there's a lot of traffic or bad weather conditions, I will probably switch over to online just to make sure that you all don't waste time driving back and forth between wherever you live in Detroit. So, okay, looks like we're a little bit over time, so thanks everyone for your attention. And like I said, any questions, please let me know. All right, have a good day, and I'll see you all on Monday.